Hi, and welcome to my garage lab. In this video, we're going to explore Le Chatelier's principle. Le Chatelier's principle says that when we have a system at equilibrium, if we stress the system in one direction or the other, our system is going to want to compensate. It's going to want to produce more of something, consume something, and reestablish that equilibrium. Now, when equilibrium is reestablished, if we have applied a bunch of stress to it, that equilibrium, as it's reestablished, may favor the reactants. Maybe it favors the products. Because remember, the equilibrium is a ratio between our products or our reactants. And so depending on what we do to one side of the equation or the other, that ratio has to adjust. So this reaction is pretty cool. It's very colorful. We're going to look at a pink hexaaquacobalt 3 ion and some chloride ions mixed together and see the type of equilibrium it establishes with the products, which is a tetrachlorocobaltate 2 ion that is blue in color and some water. All right, so we're going to start off our reaction with a 0.1 molar cobalt 2 chloride. You can see from the bottle that we're already at a pink color. So our hexaaquacobalt 2 ion is simply established by dissolving the cobalt 2 chloride into water. Okay, so I'm going to put some of that here into my test tube. So you can see it's nice and pink. All right. Now, we want to try and shift that equilibrium over to the product side. In order to shift that equilibrium over to the product side, we're going to attempt to flood the reactant side. Because right now, if you look at this, it's pink. And one of our reactants is pink. So our initial established equilibrium is favoring the reactant side. So let's see if we can do something to force this over to the product side. Well, one of our two reactants is chloride ions. So I'm going to force this over to the product side by flooding my system with an excess of chloride ions. I'm going to do that by using 12 molar hydrochloric acid. Okay. So same thing, I'm gonna get my pipette here. I'll get some hydrochloric acid and I'll drop it in there. All right. Got some good blue. There's a little bit of purplish color going on, which means I've got a mix of both. So I'm gonna add a little bit more chloride. There we go. Now we've got a really good blue color, okay? All right, so now we have shifted our equilibrium to the product side, okay? Well, how am I gonna shift it back toward the reactant side? I need to add something that is either going to flood my system with so much product that it has to shift back to reactants, or I need to do something where I remove one of the reactants from the system to get it to produce more. So I'm gonna do the latter. I'm gonna add 0.1 molar silver nitrate to my system. Silver nitrate, when added to a system with chloride ions, is going to give me a precipitate, because silver nitrate, if you recall, is going to be silver ions and nitrate ions. If you remember your solubility rules, what happens if we have silver ions and chloride ions? We make insoluble silver chloride. So as we add the silver nitrate, what we should see is a solid precipitate form, which is our silver chloride, and a shift back toward the pink. Because I need to produce more chloride ions in order to reestablish my equilibrium. So let's go ahead and drop in our silver nitrate. So there you go. You can see that we're getting some return to pink, and we are getting a solid precipitate. Okay. Okay. All right. So now we've shifted our equilibrium back toward our reactants. Now, one interesting thing about this is you can notice that there's some condensation forming up toward the top of the test tube. This means that somewhere along the way, there was some heat that was involved in our reaction. So we're going to dunk this on a hot water bath and see what happens to our system. Is it going to stay pink or is it going to turn blue? And we're going to use that data to figure out whether or not this temperature change that we're seeing up toward the top here is a reactant or a product. Because remember, We can have exothermic reactions where heat is a product, or we can have endothermic reactions where heat is a reactant. So let's see what happens. Okay, we get in our hot water bath. Okay. You might be able to start seeing what's happening toward the top here. Here, I'll pick up the camera. So what's happening? What color are we getting as this is on the hot water bath? Is it staying pink or is it returning to blue? It's returning to blue. Okay, so if we're getting blue as we heat it up, that means that heat must be a reactant, because adding excess heat is now shoving our equilibrium back toward our products. Okay, so this is an endothermic reaction if heat is a reactant. Okay, which means that if I remove heat from my system, i.e. by dunking it on an ice bath, what color should we get? Should it stay blue, or do you think we'll see a return to the pink? That's going to take a moment, so I'm going to leave it there. Okay, so hopefully you're seeing what happens with our Le Chatelier's principle as we perturb our system back and forth and back and forth. You know, when we started off, we had a nice pink color, and then we flooded our system with one of our reactants, the chloride ion. And so in order to use some of those chloride ions, our system had to react to that stress and produce more product. That tetrachlorocobaltate 2 ion. The chloro is chlorine in there, okay? So we shifted it and we got that blue. We did see formation of product. Well, when we wanted to shift it back in the other direction, we removed those chloride ions from solution. So we took out one of the reactants. By taking out one of the reactants, my system needed to form more of those reactants. And so it consumed some of the tetrachlorocobaltate 2 ion and reproduced chloride ions. And as it reproduced chloride ions, it broke down those blue ions and reformed the pink hexaaquacobalt 3 ions, okay? And then we ended up with heat as a reactant. So when we heated it, we flooded our system with more reactant, so it had to form product. And then when we removed heat, we removed a reactant, the system had to reform reactants. So hopefully this visual helped you understand Le Chatelier's principle a little bit better.